Hey, everybody. All right. Well, there's one thing that we've been talking about all semester long, but we haven't really explored. And that is, what is the age of the solar system? When did this all start? When did the formation of the solar system begin? Uh, I've been giving you numbers all semester long, but where do I get that? Where do these numbers come from? The irony is, if you study the Earth, you're not actually going to get an accurate measure for the age of the Earth. The Earth is too young. The Earth is too geologically active. All the rocks on Earth formed well after the Earth formed. So by studying the geology and the rocks here on Earth's surface, you're going to get an artificially young age. So if you want to get the age of the whole solar system, you need to look at things that are older than the surface of the Earth. So if you go to, say, the moon, and you look at the oldest areas on the moon, they've been there for a very long time. They date back to 4.4 billion years. But that's not the total age of the solar system either. In order to get the age of the whole solar system, you need to go to the structures, like rocks, that formed at the very beginning of the solar system, when the very first solids started condensing out of the pre-solar disk. And those are what you call primitive meteorites. These primitive meteorites, how do you know that they're old? Well, remember the Nebular Theory, right? Remember, to go back to the little cartoon here, remember that at the beginning of the solar system, the very first little pebbles, little grains of dust and rock that formed, condensed out of the disk, and then they started accreting together to start forming the first rocks. The very first rocks are what? They look like this. They're an accretion. They're an agglomeration of a bunch of little pebbles and dust grains that all stuck together. Most of those pebbles accreted together and formed the planets and the moons, and are gone now, but some of these primitive meteorites are still around. Some of these primitive meteorites have been orbiting around the sun for the entire history of the solar system until some of them will pass too close to the Earth, they get grabbed by Earth's gravity, and they'll crash into the Earth for us to dig up and study. This is one of those primitive meteorites. This is what's called the Allende Meteorite. It crashed near the city of Allende, which is in northern Mexico, in 1969. Right? When these things crash, if these things crash near cities, then people see them. People see the shooting star, so they know to go look for the meteorite that's left behind. The outside of these rocks looks like this. It's been melted and recooled. This is not going to give you an accurate measure for the age. The surface of these rocks are not going to give you an accurate measure for the age because these rocks have been remelted. They've been contaminated with earth stuff. But if you cut into these rocks, you see a bunch of these little streaks and blobs and granules, because that's what the original rock formed out of, was the accretion of these little pebbles. These atoms, the atoms in these rocks, date back to the very beginning of the solar system. So if we can study these rocks and get their ages, then we get the age for when condensation started in the solar system, which is to say, we know when the formation of the solar system started. It's ironic that to get the age of the sun, you can't study the sun. To get the age of the earth, you can't study the earth. To get the age of everything in the solar system, we need to look at these little gray grains and the atoms in those minerals. The atoms that have been trapped inside this mineral are like a time capsule that tell us how old they are, and by extension, how old the whole solar system is. This is how we get the age of the solar system. But how do we do that? How does this actually work? I'm jumping to the conclusion before I've actually explained how we do this. So like I said, you study these rocks by looking at the atoms, by looking at the elements and the isotopes that are in these minerals. Okay, so a quick recap of some chemistry, right? Every element in the periodic table is defined by how many protons there are in the nucleus. Every hydrogen atom is atomic number 1 because every hydrogen atom has 1 proton in the nucleus. Every helium atom has 2 protons. Every carbon atom has 6 protons, right? The chemical behavior of these elements is determined by the number of protons in the nucleus, which is why the periodic table is organized like this. The periodic table is organized for chemical reactions, for the chemical properties, which are determined by the atomic number, the number of protons that the atom has. But there's more in a nucleus than just protons, right? There's also neutrons. And atoms of the same element can have different numbers of neutrons. When atoms of the same element have different numbers of neutrons, those are said to be different isotopes. So, for example, there are 3 major isotopes of carbon. The element carbon tells you the number of protons, right? It's carbon. All carbon has 6 protons. The number of the isotope, like say carbon-12, that number tells you the mass, the total mass of the particle, the number of protons plus neutrons. So carbon-12 has 6 protons and 6 neutrons. It's carbon, so it must have 6 protons, and then the other 6 particles are neutrons. Carbon-13 has 7 neutrons. Carbon-14 has 8 neutrons. So same element, same number of protons, same chemical reactions, right? All of the carbon in your body is mostly carbon-12 with a little bit of carbon-13 and a small amount of carbon-14. And your body doesn't know the difference or care, really. It's all carbon. It all chemically reacts like carbon. The carbon in our cells, in our DNA, the carbon in our whole bodies, it's a mixture of these isotopes, and our body treats them all the same because they're all carbon. They just have different numbers of neutrons in them. Well, some arrangements of protons and neutrons are stable, right? When you pack 6 protons and 6 neutrons into a nucleus, they'll arrange themselves in a nice stable orientation, and they'll stay that way indefinitely. If you add 1 more neutron, that's also stable, right? If you add 1 extra neutron and make carbon-13, they'll arrange themselves in a pretty stable orientation, and they'll stay that way indefinitely. But if you pack 1 extra neutron in there, if you try to pack 6 protons and 8 neutrons into an atom, this becomes unstable. There's just too many particles in too little space, and this isotope, carbon-14, is unstable. This arrangement just won't stay that way forever. Eventually, this isotope will decay. It'll break down in order to turn into something more stable. So, for example, when carbon-14 decays, it breaks down and turns into nitrogen-14 because nitrogen-14 is more stable. This is what gives rise to radioactivity. Radioactivity is caused by some certain isotopes that are not stable, and they radioactively decay to become more stable eventually. In the lingo of nuclear physics, what we say is that these unstable parent isotopes decay and turn into more stable daughter isotopes. So this is sort of like a chemical reaction where you have reagents and products, but this is a nuclear reaction where you have parent isotopes breaking down and turning into daughter isotopes. That's the vocabulary that they've come up with. I said that parent isotopes decay eventually because it takes time. Different isotopes decay at different rates. And how fast an isotope decays is measured by what's called half-life. So half-life is the time that it takes for half of the parent atoms that you start out with to decay away by half. Let me explain this a little more with a simplified example. Let's say I have this unstable parent isotope and I have 1 kilogram of it, and this isotope has a half-life of 1 year, so to make the math easy. So if I start out at the very beginning of my experiment, I take a sample of these parent isotopes, I have 1 kilogram of them, and I just set it on the desk and walk away. If I come back a year later, half of those parents will still be parents, and half of the parents will have turned into daughters, which I've color-coded green here. If I come back another half-life later, so 2 half-lives have passed, 2 years have passed, what would happen? Well, I would have a quarter of the parents would still be parents, and the other quarter will have also turned into daughters. If I come back another half-life later, then half of those parents will still be parents, half of those parents will have turned into daughters. So every time a half-life passes, you're left with half of the parents that you had before, and the rest have already been turned into daughters. So it's not a linear decay, it's an exponential decay. Every time a half-life passes, you're left with half of half of half of half of half of half of whatever you had before. How long each half-life is depends on the isotope. Different isotopes will decay faster or slower. So carbon-14 has a half-life of 5,730 years. Iron-60 decays more slowly. It has a half-life of 2.6 million years. So it takes 2.6 million years for half of that iron-60 to decay by half. This is how we find the ages of these rocks. Because this is an exponential decay, it takes many, 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 many half-lives. And even after many, many half-lives, you're still going to be left with some tiny fraction of those parents left. So that if you cut into a rock and you count up the number of parents left, you count up the number of daughters that you find, that ratio of daughters to parents, the ratio of how many daughters have accumulated and how many parents are left, that ratio tells you how many half-lives have passed. And then, from studying these isotopes in a lab, you can measure experimentally how long each half-life is, and then you can just say, well, if you take the number of half-lives times the length of each half-life, you have the age of that rock. And that's what this equation at the bottom of the screen here, that's what this is giving you. All you need to do is take a sample out of your rock, count up the number of daughter atoms you find, count up the number of parent atoms you find, divide them, and sorry, had a hiccup there. Where was I? You take a sample out of the rock. You count up the number of daughter atoms in your sample. You count up the number of parents. If you divide them, that ratio tells you how many half-lives have passed since that mineral, since that rock formed. One little wrinkle here. Because the daughter to parent ratio increases exponentially with time, how do you undo an exponent? Well, you undo an exponent with a logarithm. So you take the daughter to parent ratio plus 1, take the natural log of that, divided by the natural log of 2, that undoes the exponent, and now this first term here just gives you how many half-lives have passed. So then you just multiply by tau. Tau is the symbol for the half-life of that isotope, and now you have the full age of that rock in years. This is how you get the ages of rocks here on Earth, or on the moon, or these old meteorites. Why are we focusing so much on rocks? Well, because rocks are solid. And in a solid rock, the atoms, the parent and daughter atoms, are locked inside the rock indefinitely, right? They don't go anywhere. unless something happens to the rock, unless the rock is melted or mixed up or contaminated, right? Then if something happens to the rock, if the rock is contaminated in some way, then maybe you could lose parent or daughter atoms, or maybe some new parent or daughters could be introduced, and that would throw off your count of parents and daughters, and that would make the age unreliable. This is why we focus so much on these old meteorites, because like I said, the inside of those meteorites are made of dust grains and pebbles that have been locked up inside those rocks for the whole history of the solar system until they crash into the Earth for us to find. You cut into the rock, you take the inside of the rock, because the inside hasn't been contaminated with Earth stuff yet, and that tells you the age of those rocks, which tells you the age of the whole solar system. If you want to do this really, really well, which, if you're trying to figure out the beginning of the solar system, you want a really accurate calculation there. What do? Well, make several calculations. Take several pairs of daughters and parents. Calculate the age of the rock using all these different parent isotopes. And if all of the measurements agree, then you know you've got a really reliable measurement. This is why we're so confident that we know the age of the solar system, because when you take lots of different daughter and parent pairs from these primitive meteorites, they all max out at 4.6 billion years old. Why do they all agree? All these different meteorites measured with all these different isotopes, they all max out at 4.6 billion years. Because that must be when all these rocks first started forming. Because that's when all rocks first started forming in the solar system. That must be the age at which this all started. This is how we get real numbers for areas on the Earth. It's how we get ages for different areas on the moon, because we have samples of these moon rocks. We even have some rocks from Mars that we can do this to, so that we can measure the age of areas on Mars. The only way to do this, the only way to get the ages with high precision, is to actually have rock samples. And we have rock samples from Earth, from the moon, from Mars, from these meteorites. Not much else. So a lot of work right now, and for the next many years, is going to be, let's get rock samples from elsewhere in the solar system, from asteroids, from other planets, from comets. Get samples so that we can calculate the different ages and get a much clearer idea of how old everything is in the solar system. To get an age, to get a sense of the order of when things happened in the solar system. As of now, the age of the solar system we have quite a reliable calculation of. Exactly what happened and when from the beginning of the solar system to today takes some more work, and that's an active area of research today. But whether you're studying Mars or the moon or Earth or these little meteorites or comets or maybe the moons of the Jovian planets, the process is still the same. This radiometric dating of counting up daughter and parent atoms is fairly straightforward. It's just the getting the rock samples from across the solar system. That's the hard part. But that's something that people are working on currently and probably will for a great while longer. But this is how you do it. So that's how we get the age of the solar system.